OSO 7 OSO 7 or Orbiting Solar Observatory 7 NSSDC ID 1971-83A, before launch known as OSO H, is the seventh. OSO 7 was launched from Cape Kennedy, now Cape Canaveral, on 29 September 1971 by a Delta IX rocket into a 33.1 inclination, low Earth initially 321 by 572 km orbit, and re-entered the Earth's atmosphere on 9 July 1974. It was built by the Ball Brothers Research Corporation BBRC, now known as Ball Aerospace, in Boulder, Colorado. While the basic design of all the OSO satellites was similar, the OSO 7 was larger. Total spacecraft mass was 635 kg 1397 lb than the OSO 1 through OSO 6, with a larger squared-off solar array in the non-rotating sail, and a deeper rotating section, the wheel. Sail instruments. The sail portion of the spacecraft, which was stabilized to face the Sun in all the OSO series satellites, carried two instruments on OSO 7 which continuously viewed the Sun during orbit day. These were the GSSC X-ray and EUV spectroheliograph covering the wavelength range 2 to 400A under the direction of P.I. Dr. Werner M. Neupert of the NASA GSFC, which imaged the Sun in the extreme ultraviolet and soft X-ray bands to determine the temperature and distribution of matter in the corona above active regions and during solar flares. The NRL white light coronagraph and extreme ultraviolet corona experiment directed by Dr. Richard Towsey of the U.S. Naval Research Laboratory, which imaged the wild light corona using an occulting disk, allowing comparison between the structure of the corona and the active regions on the solar surface. Wheel instruments. The rotating wheel component of the spacecraft, which provided overall gyroscopic stability to the satellite, carried four instruments which looked radially outwards and scanned across the Sun every 2 seconds. Two of these were solar observing instruments, and the other two were cosmic X-ray instruments. Oxt Hard Solar X-ray Monitoring Instrument, P.I. Prof. Lawrence E. Peterson, covered the two 300 keV energy range using proportional counter and NA scintillator detectors, plus 3 small charged particle detectors for monitoring the local radiation environment. UNH Solar Gamma Ray Monitor, P.I. Prof. Edward Chupp, observed 0.310 MeV solar flare gamma rays with a Na-Atoll scintillation spectrometer in a CS inactive anti-coincidence shield. MIT Cosmic X-ray Experiment, P.I. Prof. George W. Clark, observed cosmic X-ray sources in the range 1.5 to 9A. This instrument used proportional counters to observe cosmic X-ray sources in the 1 to 60 keV range in 5 broad logarithmically spaced energy bands, with about 1 deg angular resolution. Oxt Cosmic X-ray Experiment, P.I. Prof. Lawrence E. Peterson. This instrument, which had a field of view FWHM about 6 deg, looked out perpendicular to the wheel spin axis, sweeping a great circle on the sky every 2 seconds. As the wheel spin axis moved to keep the sail instruments pointed at the Sun, it scanned the whole sky every 6 months. It featured a 1 cm thick Na-Atoll scintillation detector that covered the energy range from ~7 keV to ~500 in 100 to 68 channels, with an effective area of 100 cm2 at the lower energies. The detector was enclosed in a thick CS in an anti-coincidence scintillation shield with 10 holes bored through it, which defined the optical field of view of the detector. Events were individually recorded and telemetered, with time and pulse height tagged for each at a maximal rate of 3.2 per second. Scientific results. Among the notable scientific results from OSO 7 were all sky-hard X-ray surveys by the MIT and Oxt Cosmic Instruments, the first observation of solar gamma-ray G-line emission due to electron/positron annihilation at 511 keV from solar flares in early August 1972 by the UNH spectrometer. Long legendary in NASA due to the hazard to human spaceflight, it would have incurred a potentially fatal radiation dose had astronauts been in space at time and outside the Earth's protective magnetosphere, as is the case during much of a lunar Apollo mission. The first clear detection of a coronal mass ejection CME by the NRL instrument. Observations of the hard X-ray spectra of the AGN NGC 4151 and SEN8 and SEN8, 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 SEN, SEN8, SEN8, SEN8. Position and spectral variability of the 14 May 1972 cosmic gamma ray burst. Near loss at launch, launch, at launch, launch. The OSO 7 was nearly lost at launch due to a loss of hydraulic pressure in the second stage guidance control system tilde 7 seconds prior to second stage engine cutoff. The nominal plan was for the spacecraft to be separated from the second stage with the spin axis normal to the sun direction so that the sail could be oriented to the sun, allowing the batteries to be fully charged on orbit. As it was, the orbit was slightly eccentric instead of circular, and the orientation of the spacecraft immediately after launch was unknown, so that the sail could not acquire sun lock. The spacecraft was launched with its batteries fully charged, giving approximately 12 hours for the controllers, directed by NASA's John Hull, to recover before the spacecraft lost power and command ability. Several hours passed as engineers attempted to interpret the signal strength from the tumbling spacecraft in terms of its transmitting antenna pattern. Finally, an hour or two before the end, Hull decided to abandon caution and start slewing, and by luck and skill, control was regained. Because the resulting orbital apogee was tilde 572 km instead of the planned tilde 350 km for the nominal circular orbit, several times each day OSO 7 passed fairly deeply into the Van Allen radiation belts so that bombardment by high-energy protons made it somewhat radioactive. The activity then decayed slowly during other times of the day. The complexly varying instrument internal radioactivity complicated the analysis of data from the sensitive X-ray and gamma-ray instruments on board. 78-1. The flight spare for OSO H was later acquired by the U.S. Air Force, modified and re-instrumented, and then launched in 1979 as 78-1, also known as Solwind, the satellite which was shot down by the USAF in a successful anti-satellite missile test in 1985. OSO 7 and 78-1 were not identical in appearance, but more similar to each other than either were to the earlier OSO 1 through OSO 6 spacecraft or to the final OSO 8.